This is a test of pure logic. A crow stands in front of a narrow tube filled with water. At the bottom, just out of reach, a small piece of food floats quietly. The bird cannot reach it with its beak. It cannot break the tube. It cannot simply force its way to the prize. So it stops. It looks. It studies the problem. Beside the tube is a small pile of stones. The crow picks one up, drops it into the water, and watches the surface rise. Then another stone. Then another. Each drop brings the reward closer. Finally, the food reaches the top. The crow grabs it. The puzzle is solved. So here is the question: is this bird smarter than a 7-year-old human? For a long time, we would have laughed at that idea. For generations, bird brain was an insult. It meant small-minded, simple, foolish. We assumed that because birds have small heads, they must have small minds. But biology has a way of humiliating human arrogance. Because the more we study birds, the more we realize that intelligence is not about brain size alone. It is about architecture, efficiency, density, speed, connection. A bird brain is not a weaker version of a mammal brain. It is a different operating system. And in many ways, it is terrifyingly powerful. The secret begins with neuron density. Human and primate brains are large, but their neurons take up space. Bird brains are compact. They pack huge numbers of neurons into a tiny volume. In the same amount of brain tissue, some birds can hold more neurons than many mammals. This is not a limitation. It is miniaturization. A crow, parrot, or raven is not carrying a small computer. It is carrying an organic supercomputer inside a lightweight skull. Flight demands efficiency. Every gram matters. A bird cannot afford waste. Its bones are light. Its muscles are optimized. Its lungs are efficient. And its brain follows the same rule: maximum processing power in minimum space. This is why a crow can solve problems that look almost human. The New Caledonian crow is one of the clearest examples. These birds do not merely use tools. They manufacture them. In the forest, a crow may strip leaves from a twig, bend the end into a hook, and use it to pull insects from deep holes. That requires more than instinct. It requires a mental blueprint. The bird must imagine a future result before the tool exists. It must understand that a straight object can become a hook, that a hook can extend reach, and that reach can solve a problem. In laboratory tests, these crows have solved multi-step puzzles they have never seen before. They may use a short stick to obtain a longer stick, then use the longer stick to reach food. That is sequential planning. They are not just reacting. They are thinking in steps. And once we accept that, the old insult begins to collapse. because toolmaking was once considered a human signature. Then apes joined the category. Then crows arrived, holding hooks in their beaks, forcing us to redraw the map of intelligence. But not all genius looks like tool used. Sometimes, genius is memory. The Clark's Nutcracker is a small bird with an almost impossible task. In autumn, it hides seeds across mountain landscapes. Not a few seeds, not a few hundred, tens of thousands. Some estimates suggest it may cache around 30,000 seeds in a season. Then winter comes. Snow covers the ground. Landmarks disappear. The forest becomes a white blank page. And still, months later, the bird returns. It dives into the snow and retrieves its hidden food. Again. And again. And again. Imagine remembering 30,000 passwords without a password manager. Imagine hiding thousands of tiny objects across a mountain, leaving for months, and coming back when everything looks different. That is not simple memory. That is a survival database. The bird's hippocampus, a brain region important for spatial memory, changes with the demands of the season. Its brain is not fixed. It adapts to the work it must do. This is intelligence shaped by winter. Then there is numerical competence. Can birds count? The answer is more uncomfortable than many people expect. Pigeons can be trained to arrange visual quantities in order. Parrots can understand concepts like more, less, same, different, and even zero. And zero is not easy. The concept of nothing as a value is a major cognitive leap. To recognize zero is not just to see an empty space. It is to understand absence as information. A bird looking at an empty tray and treating it as a numerical category is not behaving like a machine. It is processing an abstract idea. And abstraction is one of the foundations of higher intelligence. Perhaps the most famous example of avian cognition was Alex, the African gray parrot, studied by Dr. Irene Pepperberg. Alex did not simply mimic sounds. He learned to identify colors, shapes, materials, and numbers. He could answer questions about objects. He could distinguish same from different. He could use words with meaning. One day, looking into a mirror, Alex asked, "What color?" He was asking about himself. That moment changed the conversation. It suggested that at least some birds were not merely repeating human speech. They were connecting words to concepts, concepts to objects, and perhaps objects to self-awareness. Alex's final words to Irene were reportedly, "You be good. I love you." Whether we interpret that as emotion, learned language, or something in between, it is difficult to dismiss. It reminds us that the emotional world of birds may be deeper than we once allowed ourselves to believe. Self-recognition adds another layer. The mirror test is one of the classic ways scientists study awareness. Many animals see their reflection and treat it as another creature. But magpies have shown behavior suggesting they can recognize themselves. When a mark is placed on a part of the body they cannot directly see, a magpie may use the mirror to find and remove it. That means the reflection is not just another bird. It is me. A sense of self, emerging through a completely different evolutionary path. This is the key point. Birds do not have a mammalian neocortex like ours. For a long time, scientists assumed that without that layered structure, advanced thought must be impossible. But birds use different brain regions, especially parts of the pallium, to perform complex processing. Different hardware, similar output. Evolution found more than one way to build a thinking mind. In corvids and parrots, brain regions involved in planning, decision-making, impulse control, and problem-solving function in ways that resemble the role of the prefrontal cortex in mammals. The structure is different, but the result is intelligence. This should make us humble, because consciousness may not belong to one body plan. It may be an emergent property of complex networks. Bird intelligence is also deeply social. Ravens remember relationships. They track who cooperates, who cheats, who shares, and who cannot be trusted. In their world, reputation matters. A raven that takes without giving may be remembered and avoided. Their social lives are not simple. They are alliances, rivalries, debts, favors, betrayals, and long memories. In other words, drama and social complexity drives brain growth. If you must remember not only places and objects, but personalities, histories, and intentions, your brain must become sharper. This leads to one of the most unsettling abilities of all deception. A raven hiding food may notice another bird watching, so it pretends to hide the food in one location, then secretly hides it somewhere else. This is not random movement. It is misdirection. To deceive, you must understand that another being has a point of view. You must understand what it sees, what it does not see, and what false belief you want it to form. That is close to what scientists call theory of mind. The ability to think about another mind. A bird lying about food forces us to ask a strange question: how many layers of thought are hidden inside that small skull? Urban crows show the same flexible intelligence. In some cities, crows have learned to drop nuts on roads so cars can crack them open. Even more impressive, they may wait for traffic signals before walking out to collect the food. They are not merely surviving in human environments. They are hacking them. A road becomes a tool. A traffic light becomes a safety system. A car becomes a nutcracker. This is adaptive intelligence in real time. Birds also learn from one another. Young crows can observe older birds and copy successful strategies. Songbirds practice songs. Zebra finches rehearse vocal patterns while sleeping. Scrub jays remember not just where they hid food, but what type of food they hid and when they hid it. If the food spoils quickly, they retrieve it sooner. That means they are tracking time. What? Where? When? The building blocks of episodic memory. The intelligence of birds is not one thing. It is a spectrum. Tool use, memory, counting, language, social awareness, deception, navigation, play, culture. Even play matters. Kia parrots in New Zealand dismantle objects, investigate mechanisms, and seem to explore the world with a mischievous curiosity. Play is not useless. It is training. It is experimentation. It is the luxury of a brain with spare processing power. A simple animal does not waste energy playing complex games. A smart one does. And birds are smart in different ways. An owl is not necessarily a crow. The owl is a specialist, built for silent hunting in darkness. The crow is a generalist, built to solve whatever problem the world puts in front of it. Intelligence is not one ranking. It is adaptation to a mission. A woodpecker's brain must survive repeated impact. A falcon's brain must process visual data at extreme speed. A pigeon's brain must navigate home across huge distances. A parrot's brain must connect sound, meaning, and social interaction. Each species is a different answer to the question, what does survival require? Even collective bird behavior can look like intelligence. A murmuration of starlings moves like a living cloud. No single leader controls the group. Each bird follows simple rules based on its neighbors. And together they create complex, fluid patterns. The flock becomes a distributed brain, 1,000 small decisions becoming one large movement. This is swarm intelligence. And it may inspire the future of technology. Scientists studying bird brains, flocking behavior, and avian efficiency are learning lessons for artificial intelligence, robotics, drone navigation, and energy-efficient computing. The future may be bird-inspired. The insult bird brain has become outdated. Maybe it should become a compliment. Because a bird brain is dense, efficient, fast, flexible, social, creative, sometimes deceptive, sometimes emotional, sometimes self-aware, always underestimated. When a raven looks directly into the camera, it does not feel empty. It feels knowing, as if it is watching us just as much as we are watching it. For centuries, humans placed themselves alone at the top of the mountain of intelligence. But the sky is full of geniuses. Crows solving physics puzzles. Nutcrackers mapping invisible seed vaults. Parrots, using words with meaning. Magpies, recognizing themselves. Ravens, navigating politics. Pigeons, calculating numbers. Songbirds, rehearsing in dreams. Birds are not failed mammals. They are a separate experiment in consciousness. A different path to the same light. Intelligence is not about brain size. It is about neural architecture. So the next time someone calls another person a bird brain, maybe they should be careful. Because somewhere, a crow is solving a problem. A parrot is naming a color. A raven is planning a trick. A nutcracker is remembering a mountain. And the sky itself is thinking. Stay curious.